Hey everyone, and welcome to This Explainer. Today, we are diving straight into the absolute extremes of propulsion. We're going to frame this whole discussion as the ultimate exercise in constraint-driven engineering and resource management. So if you manage projects, build complex systems, or honestly, if you just love understanding how massive machines conquer the laws of physics, you are going to love this. We're pitting the air-breathing jet engine against the vacuum-conquering rocket engine. Now, both of these engineering marvels actually share the same fundamental goal, right? They push a vehicle forward by throwing mass out the back as fast as humanly possible. But because they operate in completely different environments, their engineering paths diverge in ways that are just absolutely fascinating. So, let's dive into this epic battle of system redundancy and efficiency versus sheer brute force power. Okay, I want to kick things off by immediately hitting you with this staggering number, 90%. Just let that sink in for a second. Up to 90% of a rocket's total launch weight is literally just its fuel and oxidizer. Before you can even think about the payload, the astronauts, or the actual metal structure of the vehicle itself, you have to surrender 9/10 of your mass budget just to carry the chemicals that make the fire happen. This introduces the absolute most critical constraint in aerospace engineering, the mass ratio. That's the ratio of a vehicle's initial mass when it's fully fueled compared to its final mass when it's empty. It's often called the Achilles heel of rocketry, and for good reason. When you're fighting gravity, every single gram matters, and rockets are basically cursed by having to carry a tremendous amount of extremely heavy liquid just to get off the launch pad. And this brilliant little equation here perfectly illustrates the fundamental difference in resource management between the two engines. Let's do a quick thought experiment. Picture a standard commercial Boeing 747 jetliner. What if, instead of just loading it up with jet fuel, you also had to load it up with giant, heavy tanks of liquid oxygen so it could actually burn that fuel? Well, the plane would be way too heavy to ever take off. The absolute genius of the jet engine is its ability to offload the immense weight of the oxidizer to the atmosphere. A jet engine is an open system. It carries its fuel, sure, but it borrows its oxidizer, the air, from the environment as it flies. A rocket, on the other hand, operating in the vacuum of space, it's a closed system. It has to bring absolutely everything with it. So it's absolutely crucial to understand exactly what this burden is. An oxidizer is simply the chemical agent that supports combustion. Without it, your fuel is just not going to burn, no matter how hot it gets. And since there's no air in space, rockets have to lug their own oxidizer along, usually in the form of liquid oxygen, or LOX. To really grasp the sheer scale of this weight penalty, let's look at the space shuttle. The shuttle's external tank carried about 100,000 kilograms of liquid hydrogen fuel. But to burn that fuel, it had to carry an astonishing 610,000 kilograms of liquid oxygen. I mean, that is a fuel-to-oxidizer ratio of roughly 6:1. The heavy structure required to hold over 600,000 kilos of liquid oxygen adds a massive weight penalty that jet planes just completely avoid. Part 1. Jets, the efficiency masters. Because jet engines don't have to carry their own oxygen, they become absolute masters of efficiency. They aren't fighting that oppressive mass ratio of a rocket, which allows them to be optimized for reliability over literally thousands of hours of continuous operation. Now, this thermodynamic loop you're seeing here maps out their heartbeat. It's called the Brayton cycle. Unlike the engine in your car, which has those pulsed strokes for intake, compression, combustion, and exhaust, the Brayton cycle is all about continuous combustion. As you can see from that compression loop on the left side of the diagram, the engine is continuously scooping up air from the atmosphere, mechanically compressing it using a massive rotating fan, adding fuel, igniting it at constant pressure, and then exhausting it out the back. It's just a highly elegant, continuous flow of energy conversion. But here's the really cool part. The atmosphere actually gives the jet engine an operational free lunch that goes way beyond just providing free oxygen. The air we breathe is actually about 78% nitrogen, which is mostly unreactive during this whole combustion process. So, when a jet engine sucks in air, all that nitrogen acts as a massive thermal buffer. It dilutes the combustion reaction and naturally lowers the temperatures inside the engine. Plus, just the sheer volume of air flowing around and through the engine acts as a natural cooling medium. The jet engine is effectively cradled and protected by the exact environment it flies through. Part 2. Rockets, the thermal nightmare. Unlike jets, a rocket operates in the vacuum of space. It gets absolutely zero thermal help from its environment. Because it carries pure liquid oxygen instead of atmospheric air, there is no unreactive nitrogen to dilute the reaction. The combustion temperatures in a rocket engine can actually reach true stoichiometric levels, which just means the fuel and oxidizer react perfectly to release the maximum possible heat. Now, this sounds fantastic for performance, but it's an absolute nightmare for metallurgy. These temperatures easily skyrocket right past the melting points of the metals used to build the engine itself. For example, copper, a highly conductive metal they often use in combustion chambers, melts at around 1200 Kelvin. A rocket burns much hotter than that. If engineers aren't careful, the engine will literally melt itself into what the aerospace industry jokingly calls an engine-rich exhaust. So how on earth do you contain a fire that is literally hotter than the melting point of your own engine? Well, engineers use two primary strategies here. The first is ablative cooling. They line the inside of the engine nozzle with these specialized carbon composite materials. As the engine burns, this layer intentionally vaporizes, which absorbs the extreme heat and carries it safely away in the exhaust. It's incredibly reliable because, hey, there are no moving parts. The second and way more common method for large liquid rockets is regenerative cooling. The walls of a rocket nozzle might look totally solid, but they're actually made of hundreds of tiny, hollow tubes. Before the super-chilled cryogenic liquid fuel is burned, it's first pumped incredibly fast through these tubes to absorb the heat from the metal walls. So the fuel actually cools the engine, gets slightly preheated in the process, and is then injected into the chamber to burn. I mean, it is just a brilliant, high-stakes piece of resource management. Part 3. The heart of the beast. Compressors versus turbopumps. Okay, so to generate thrust, both of these engines need to create immensely high pressures right before combustion. A jet engine uses a massive rotating axial compressor, those are the giant fan blades you see when you're boarding a flight, to squeeze the incoming air. But a rocket? A rocket uses something way more violent, a turbopump. A turbopump is essentially a liquid pump that's driven by a gas turbine. Its one and only job is to force massive, honestly incomprehensible amounts of liquid fuel and liquid oxidizer into a tiny combustion chamber at insane pressures. To give you some perspective on the forces at play here, the high-pressure fuel turbopump on the Space Shuttle's RS-25 engine spun at over 36,000 revolutions per minute. It was roughly the size of a V8 car engine, but it generated tens of thousands of horsepower just to push liquids against the incredible pressure of the ongoing explosion happening inside the chamber. Once that incredibly high-pressure combustion actually happens, you have to get it out of the engine to create thrust. Rockets achieve this using what's called the de Laval nozzle. It has this very specific converging, diverging shape. So the hot gas is forced through a narrow opening called the throat, which accelerates it to Mach 1, the speed of sound. Then, as the nozzle bell widens out, the pressure drops and the gas rapidly expands, dramatically accelerating to supersonic speeds. This expansion is what converts the intense thermal pressure into sheer kinetic velocity. The exhaust coming out of a rocket nozzle can literally be traveling up to 10 times the speed of sound. Absolutely wild. Part 4. Efficiency versus pure power. When we finally look at the ultimate result of these two different engineering paths, the numbers are just stark. What we're looking at here are thrust-to-weight ratios. This basically tells us how many pounds of thrust an engine produces for every pound the engine itself weighs. Let's look at the top two rows first. The J58 jet engine, the one that powered the legendary SR-71 Blackbird to Mach 3, has a ratio of 5.2. The Concorde jet engine, 5.4. And remember, these are some of the most advanced air-breathing engines ever made. Now look at the rockets. The Space Shuttle's RS-25 rocket engine comes in at 73.1. And the Merlin 1D rocket engine, which SpaceX uses on the Falcon 9, generates a mind-bending 180 pounds of thrust for every single pound of its own engine weight. Rockets just completely abandon the complex, heavy efficiencies of jet compressors and their atmospheric reliance to achieve this breathtaking brute force power. But of course, the universe always demands a toll for that kind of power. As you track specific thrust here, you'll see that the higher the performance and power output of the engine, the more rapidly the fuel is consumed. Rockets generate unbelievable thrust, sure, but they guzzle their propellants at truly terrifying rates to make it happen. And this circles us perfectly back to that massive weight constraint we started with. Because rockets burn through fuel so quickly to achieve that massive thrust-to-weight ratio, they have to carry tens of thousands of gallons of it, making the vehicle 90% fuel by weight. So, I want to leave you with this final thought. I think it perfectly frames the operational constraints we've explored today. Imagine, you're an engineer managing these resources. You have to ask yourself, do you want to build an open system that perfectly uses its environment to fly reliably and efficiently for 10,000 hours? Or do you want to build a closed thermal nightmare that completely abandons all efficiency just to touch the stars for 10 short minutes? Both are absolute masterpieces of human ingenuity, but they are completely defined by the constraints of their environment. Thanks so much for joining me on this explainer today, and remember to always keep questioning how the world around you is built.